Circular motion 5. A car of mass m drives toward us. So here it comes. Out of the page at a speed v. The car is on a level surface in uniform circular motion with the circle's center at the leftmost edge of this page, the distance r from the car. The center of the path, if you can see on the very left side of this video, see, there's the center of the path. And so the car is coming towards us, and then it's going to go, as it gets, it's going to curve like this. All right. Which means this car is going to be accelerating that way. That's the way it's going to be accelerating, because there's the center and around the car goes. All right. The force that makes the car move in a circular path is friction. And it is much more like static friction than kinetic friction because there's no sliding. In order to have kinetic friction, you have to have sliding, and we don't have sliding here. Therefore, here we will give the frictional force the familiar label of F sub s, static friction. Normally, there is no always works equation that applies to this friction force. We've talked about how the static friction force, sometimes it's 0. Sometimes it's a little bit more, maybe a little bit more, maybe a little bit more, and then all of a sudden it's maxed out. However, when this force is maximized, as we will assume below, it conforms to the equation mu sub s times the normal force. If it's maxed out, then we have an expression for the static friction force being mu sub s multiplied by the normal force. Assuming mu sub s is known, derive an expression for Vmax, the fastest turning speed the car can have on radius r and not slide. You see, if it goes faster than that, then it's going to start to slide, and then we don't have static friction anymore. So static friction is going to be maxed out. So let's draw a free body diagram here. There's the mass of the car. Gravity pulls downward. Then we have a normal force that acts upward. And isn't it true? We don't always do this, but I'm going to here. Those two are numerically equal, aren't they? And then there is a static friction force. We said that this car was going to have to accelerate to our left, because over here on the far left side of the video, that's where the center is. This car has to be accelerating towards the center, and the force that is causing that is static friction. Now, static friction is maxed out. We just wrote this on the last paper. Then we know the expression for it, mu sub s times normal force. And if normal force is equal to mg, then can't we further simplify that to be mu sub s m times g? So let's use Newton's second law. What's the net force? The normal force and the weight cancel. So the net force is just mu sub s mg. And that needs to equal the mass of this car times its acceleration. If we are going through centripetal acceleration, we've said that the acceleration is numerically equal to v squared divided by r. And we want to solve for v. The m's cancel like that. I'm going to put the r on the other side. You check and make sure I've done this correctly. I think I'm getting here mu sub s times g times r. Take the square root of the whole thing. Maybe I should say Vmax. That's the maximum speed that something can have without slipping. And you can see it depends on the coefficient of friction, and it depends on the radius of curvature, but it doesn't depend on the mass.